Okay, so you are working for the summer. Your research director has devised a scheme for trapping particles. So we have a large sphere of radius r, or radius a. With a small tunnel drilled through the middle. So it's radius a. And here's our two particles, which are trapped at a distance of r from the center. And the particles have a charge q, and the whole sphere has a charge q. Okay, so this is an application of Gauss's law. So Gauss's law is just that our electric field times our area is the charge enclosed by the area over E naught. So for the first part here, our area is just going to be the surface area of a sphere which encloses the charges. So our surface area is 4 pi r squared. Our charge enclosed, so it's a uniform charge density. So our charge enclosed is our rho times our volume, which is rho times 4/3 pi r cubed. So that our electric field is rho 4/3 pi r cubed over 4 pi r squared E naught. We can cancel much of this and get rho r over 3 E naught. Our rho is our charge density, which is our total charge over our total volume. So then putting that into our electric field, we get charge R over 3 E naught times 4/3 pi A cubed. So the 3's will cancel. And we get QR over 4 pi E naught A cubed. So that's our electric field at a point R. So then our force on a charge Q is just QE. So that'll be QR over 4 pi E naught A cubed. So that's our force on a charge. We have two of these charges at distance 2r from each other, so then we also have our charge force, which is Q over 4 pi epsilon naught r squared. In this case, our r is 2r. So if we look at the figure, so our charge repulsion is Q1, Q2, and both have a charge. I should put these in here just to differentiate a little bit. So both charges have Q1 is equal to Q2 is equal to Q. So our charge repulsion is then just q squared over 4 pi epsilon naught times 2r squared. Okay. So then our net force is the sum of these two. So Q R over 4 pi epsilon naught A cubed plus Q squared over 4 pi epsilon naught times 2R squared equals 0. So it equals 0 if they're in equilibrium. So we're asked to find equilibrium values for R. Equilibrium values for R. So now we need to rearrange things. So first of all, we can get rid of a Q, get rid of a 4 pi epsilon naught. So that'll help a little bit. So then let's migrate some things and expand some brackets here. So we've got Q R over A cubed is equal to minus Q over 8, sorry, not 8, 4R cubed, 4R squared. So now bringing the r's around, so r cubed is equal to minus q a cubed over q. And so r is minus q a cubed over q to the 1/3. So now this is a negative sign, meaning that our radius would be negative, so that's not possible. So only positive for q less than 0. So our big Q is given in the question as positive, so the little q's must be negative. So must have, we must have Q equals minus Q, or Q negative, in other words. So the particles must be negatively charged. If they're negatively charged, then our R's would be positive, and it would be given by this value. Okay, so now we want to extend the system by adding little tubes. So we have our sphere, and then we want to extend outside the sphere and put the particles out here. So again, we have our sphere of radius A, and now the particles are being separated by much larger distance. And wonders if we can still do it, or they can still wait. They're still in equilibrium position. So in this case, the only difference is that, again, our E field times our area is the charge enclosed over E naught. In this case, our charge enclosed is our total charge, as at this radius we're enclosing the total charge at all times, but our area, our surface area, is still going to be this 4 pi r squared. So then our E field is just Q over E naught 4 pi r squared. And so then our force on our particles is going to be Q over 4 pi epsilon naught r squared. Okay, and then our force on our two particles is still going to be the Q squared over 4 pi epsilon naught times 2r squared. Summing our two forces and setting the acceleration to 0. To r squared is equal to 0. Will allow us to solve this here, or solve for the equilibrium. Again, we can cancel 4 pi epsilon naught, and now and one of the q's we can rearrange here. So we've got minus q over 4r squared is equal to q over r squared. So then the r squares will cancel, and that means then that there's an equilibrium at any r as long as q equals 4q minus. So as long as our charge is minus 4 times the total charge, there's an equilibrium at any r. So you can put the particles literally anywhere, but the charge in the tiny particles has to be 4 times that of the charge in the whole surface. Okay. Checking through the solution here. So we get that our r is minus q. Oh, I guess I could have brought the a out. Oh, I did drop the 4. My apologies. So that 4 just kind of disappeared. So there should be a 4 here and a 4 here. So I dropped the 4 right at this point here. So yeah, it should be qa cubed over 4q. So that looks good. So they just brought the a out, which I could have done. So this would be minus q over 4q to the 1/3 times a. So that's doable. So that at least there's different r's depending on the charge. And then down here, we get that there's any equilibrium at any position as long as q is minus 4q. So that looks good. Okay.